Hi, I'm Sean Gannon, and this is Minute Math, and today we're learning about intervals of concavity.
Minute Math, when you need help you use Minute Math.
We're given this problem right here, y equals x to the third power minus 3x squared plus 4, and we want to find the x-coordinates of all the points of inflection, the discontinuities, and the intervals where the function is concave up and concave down. Now we have our polynomial function here, and it really is continuous everywhere. So right off the bat we can say no discontinuities. If I can spell discontinuous, I spell right, exist. Got that off the bat. Alright, so to find our, point of inflection there, we need to take the second derivative. So we'll take the first derivative, pretty easy with power rule, f prime of x here. 3 comes down, 3x squared, minus 3 times the 2 comes down, 6x, and derivative of the constant for 0. Keep going, we have to find the second derivative here, so f double prime of x here. 2 comes down, times 3 is that 6x to the first power now, and we just have minus a 6 here. We now have to take the second derivative, set it equal to 0, 6x minus 6 equals 0, and we're solving for x. Add a 6 to both sides, 6x equals positive 6, divide both sides by 6, and x equals 1. And so our inflection point here is, well, actually, we have to actually see what's the point of inflection, right? So let's use our table, put a 1 right here, okay? And we plug it into into our second derivative, and we find a value less than 1 and greater than 1. This is our second derivative test. So f double prime of value less than 1, I chose 0, and I got a negative 6. All I care is that it's negative, and that means we're concave down here. F double prime of value greater than 1, I picked 2, and that's a positive 6. And it's positive, meaning we're concave up. So our point of inflection, we change concavity, is x equals 1. And now let's say the intervals where we're concave up and concave down. We're concave up on the interval from 1 to positive infinity, and we're concave down from negative infinity to positive 1. And so again, our final answer here is there's no discontinuities exist. Our inflection point is at x equals 1. We're concave up from 1 to positive infinity, and we're concave down from negative infinity to positive 1. We're given this problem right here. Y equals x to the third power minus 2x squared minus 2. And we want to find the x-coordinates of the points of inflection, discontinuities, and the open intervals of the function where we're concave up and concave down. Now we have a basic polynomial function here, and we know it's actually continuous everywhere. So we would say right off the bat that no discontinuities exist. Right? So no discontinuities exist here. Now to find my points of inflection here, I need to take the second derivative, but I first need to take the first derivative. So f prime of x here, of our function, power rule, 3 comes down, x subtract the exponent by 1 is a 2, minus 2 times 2 is the 4, x subtract the exponent by 1, so it's a 1, that's it. Derivative of constants, just 0. From there I need to find my second derivative, f double prime of x. Power rule comes down, 3 times 2 is a 6, x to the first power minus just the 4. I now take my second derivative and I have to set it equal to 0. We have a 6x minus 4 equals 0. Add a 4 to both sides. We have 6x equals 4. Divide both sides by 6, and x equals a 2/3 when we simplify that. So now I need to do my second derivative test. I take 2/3 here, 2/3, and I need to plug in a value less than 2/3 and greater than 2/3 into my second derivative. I picked for my second derivative 0, and I got an output of negative 4 when I plug it into the second derivative. From there, that says, well, I only care that it's negative, and that means we're concave down here. I take my second derivative again, plug a value greater than 2/3, and I picked 1, and that came out to be a positive 2. It's positive, that's all that I care about, and that means it's concave up. And again, that's a second derivative test. So now we have all the information we need to answer this problem. Our point of inflection, where we change concavity, is a 2/3. So I would say inflection point x equals 2/3. Our concavity, we're concave up on the interval from 2/3 to positive infinity, but we're concave down on the interval from negative infinity to a 2/3. And so again, our final answer here is no discontinuities exist. Our inflection point is at x equals 2/3, and we're concave up from 2/3 to positive infinity, and concave down from negative infinity to positive 2/3. We're given this problem right here. Y equals x to the 4th power plus x to the 3rd minus 3x squared plus 1. And we want to find the x-coordinates for all the points of inflection, discontinuities, and the intervals where the function is concave up and concave down. Well, first thing I noticed that this is just a basic polynomial function, meaning it's continuous everywhere. So right off the bat here, I can say no discontinuities exist. Pretty straightforward. Now, to find where our point of inflection and we're concave up and concave down, we need to find the second derivative. So to do that, I take my function, I'm going to find the first derivative first. Power rule, 4 comes down, x to the 3rd power, pretty easy. 3 comes down, x squared, not too bad, and 2 times 3 is a 6. So we have minus 6x here. And that's it, derivative 1 is 0. From there, I need to find the second derivative, f double prime of x. And so, again, power rule, 3 comes down, 3 times 4 is 12, x squared, plus 2 times 3 is 6x, and then we have minus a 6 here. Now to find my point of inflection, and where we're concave up, concave down, I need to take a second derivative and set it equal to 0 and solve for x. So 12x squared plus 6x minus 6, I set equal to 0, and now I'm solving. Now, right off the bat, I'm just going to pull out a 6 here from everything. I found it a little easier. And I'm left with a 2x squared plus 1x minus 1 equals 0. Divide both sides by 6. We don't really, kind of eliminates that, right? We have 2x squared plus x minus 1 equals 0. And with factoring, I find that a little easier. This factors to be a 2x minus 1 times an x plus 1. And then from there we set each parenthesis equal to 0 and solve. 2x minus 1 equals 0, and x plus 1 equals 0. Here, subtract 1 on both sides, 2x equals 1, and x equals a 1/2. Subtract 1 on both sides, and x equals a negative 1 here. So we have 2 points here. We need to make our little chart for the second derivative test. So, make my chart right here, within the bounds. Okay. And from there, I start with the negative 1 and 1/2. And our second derivative test here, we need to plug in values into our second derivative and see if they're positive or negative that are within these intervals. So I picked negative 2, so I said f double prime of negative 2, and that came out to be a positive 30. Did I get my spot right? Yeah. I don't care what the number is, I just care that it's positive, and that means we're concave up here. Between negative 1 and 1/2, I picked 0, so I said f double prime of 0, plugged it into my second derivative, and I got a negative 6 here. That means we're negative, that's all I care about it, and it's concave down. Lastly, we have 1/2. Well, I'll pick a value just bigger than 1/2. I picked f double prime of 1, and that came out to be, plugged into my second derivative, a 12. It's positive 12, concave up. And so now we have everything we need. We have our point of inflections where we change concavity from negative 1, or at negative 1 and at 1/2. So we'd say our inflection point is at x equals -1 and a positive 1/2. We are concave up. All right, the intervals where we're concave up are from -infinity to a -1 and from a 1/2 to a positive infinity. And we're concave down from the interval from -1 to a positive 1/2. So just review our answers here. No discontinuities exist. Inflection point is from x equals, or at x equals -1 and a 1/2. Concave up from -infinity to -1 and 1/2 to positive infinity, and concave down from -1 to 1/2. We're given this problem right here, y equals 1 over x minus 3, and we want to find the points of inflection, discontinuities, and where the function is concave up and concave down. Now we have a rational function here, and the first thing I'm thinking about is, where's that asymptote? Well, it happens when we're dividing by 0. So I take my denominator, x minus 3, and set it equal to 0, and I have x equals a positive 3. And that's where our function is discontinuous, all right? The only time it's discontinuous. So we have a discontinuity at x equals 3. So we have a discontinuity at x equals 3 right there at that asymptote. Let's keep that in mind here. Now, to find our points of inflection and where we're concave up and concave down, we need to find the second derivative. And to do that, we need to find the first derivative. And I actually like to write my function, when I take a rational function just like this, I like to write it x minus 3 to the -1 power, just a personal preference. I find it easier to find the derivative. F prime of x here, power rule, -1 comes down, x minus 3 stays the same, -2 in the numerator, or sorry, in the exponent, and multiply by 1 here, derivative the inside. Well, we can really kind of simplify this. F prime of x is equal to a negative x minus 3 to the -2 power. Well, now let's go find the second derivative. F double prime of x equals, well, we have a negative, well, 1, I'll rewrite that here. Power comes down, -2. X minus 3, subtract the exponent by 1, -3, derivative inside is just a 1. Simplify this out, f double prime of x here. -1 times a -2 is a positive 2, times 1 is 2. Keep that in the numerator. Denominator, we bring down that x minus 3 to the positive third power. Okay, so now what we want to do is, we have our second derivative. We need to find, well, our kind of points of inflection, a critical point here really with that. And that's going to happen when the denominator is equal to 0. That's something critical that's happening. So we take our x minus 3 to the third power, and I set it equal to 0. Well, third root both sides really don't matter anything. Third root is 0, so we have x minus 3 equals 0, and x equals positive 3. And notice we also had that with our discontinuity at the same point. Keep that in mind. So we're going to use our second derivative test, and 3 is going to be our point here. Plugging into our second derivative, f double prime, I picked 0 to be less than 3, and I got a negative 0.0741, which really only matters because over the negative part, that's all we care about. And we're concave down. Pick the value bigger than 3, which was 4, f double prime of 4, and that came out to be 2. It's positive, that's what I care about, and we're concave up. So here's a tricky point. Right off the bat, you want to say, okay, concave down, concave up, point of inflection, but not true. We have an asymptote at 3, and we can't have a point of inflection there because we have an asymptote. So we would say actually that no inflection point points exist there. But we can tell intervals where we're concave down and concave up. We're concave up from the interval of 3 to positive infinity, and we're concave down from -infinity to 3. And so, again, our final answer here is we have a discontinuity at x equals 3. No inflection points exist. Concave up from 3 to positive infinity, and concave down from -infinity to 3. We're given this problem right here. y equals a negative x to the third power over x squared minus 4. And we have to find the points of inflection, discontinuities, in open intervals where the function's concave up and concave down. Now, what we want to do here, I first want to find where it's discontinuous. And since this is a rational function, it happens when the denominator is really going to be equal to 0. So I take that x squared minus 4 set it equal to 0, put a little note here, it's kind of easy to do. X squared equals 4, x equals plus or minus, well, square root of 4 to both sides, right? Or square root of both sides plus or minus 2. So we have a discontinuities, we can write it out here, discontinuities at x equals negative 2 and positive 2. And we'll keep that in mind, okay? We'll keep that in mind there. So now we've defined the points of inflection and its concavity doing the second derivative test. And we need to find the second derivative first. So to find the first derivative on the way there, f prime of x, we're going to use our quotient rule. All right, negative stays out front here. And we have derivative of the numerator. We have 3x squared times the denominator, x squared minus 4, minus derivative denominator, 2x, times the derivative the numerator itself, 3x squared. Oh, sorry, x squared, not 3x squared. That's a derivative. X to the third power. Almost messed this whole thing up. Okay, pay attention to my notes carefully here. Denominator squared, x squared minus 4 squared. All right, let's simplify where we can. F prime of x here. All right, negative stays out front here, but 3x, we just multiply this out, right? 3x squared times x squared is 3x to the fourth power. Let's make sure that's over right here. Okay, just so I don't forget that negative there. And then 3x squared minus times a negative 4 is a negative 12x squared. And then 2x times x to the third power is x to the fourth power, 2x to the fourth power, subtract that, 2x to the fourth power. And our denominator is still that x squared minus 4 all squared. Again, let's simplify this one more time. F prime of x is equal to the negative stays out front, but we have 3x to the fourth power minus 2x to the fourth power, and we just have x to the fourth power. And again, that minus stays there. And then we have a minus 12x squared here, all over that x squared minus 4 all squared. Okay. And here's where we're going to do the second derivative, and it gets kind of crazy here. Okay? So again, we're using the quotient rule. Let's do f double prime of x, and let's take our time here. Follow the same process, you'll get it. Negative will stay out front, but the quotient, we take the derivative numerator, which is a 4x to the third power minus a 12 times 2 is 24x, times the denominator, x squared minus 4 all squared, minus the derivative of the denominator, which is a power rule, chain rule thing going on here. So 2 times an x squared minus 4, subtract the exponent by 1, we're good, times the derivative inside, which is a 2x, right? Yeah. Times the numerator, which is just that x to the fourth minus 12x squared, all over the denominator squared. X squared minus 4 squared squared. Okay, let's go simplify where we can. So we have f double prime of x here. Negative, don't forget that negative out there. When I was doing the notes here, it kind of got me. Now notice here, I'm actually seeing an x squared minus 4 and x squared minus 4 and kind of this whole multiplication, and then down here. So I'm going to pull that out first. So I'm going to pull out an x squared minus 4. And again, how do I do this? That minus sign I like to put with right next to the division symbol. Put a bracket, okay? And here I kind of simplified what we have left over. So if I pulled out that x squared, or a minus 4, we have 1 left over here, and this one gets kind of canceled out. So I don't have to worry about that, so I don't get confused. Multiply 4x to the third times x squared, and that's a 4x to the 5th power. Got that? 4x to the 3rd times a minus 4, minus 16x to the 3rd power, minus 24x times x squared is a minus 24x to the 3rd power. Negative 24x times a negative 4 is a positive 96x. Then multiply this all out. Well, 2 times 2x, let's combine these two here, and we have a 4x right there. Okay, so multiply that, 4x times an x to the 4th power here. 4x times x to the 4th power is we have a minus here, 4x to the 5th power. And then negative 4x, right, because we're minusing, negative 4x times a negative 12x squared is a positive 48x to the 3rd power. Bracket complete. Oof. Over the denominator, x squared minus 4, and raise a double exponent, multiply 4. 2 times 2 is 4. Now, we at least can cancel this one thing out, makes it a little easier. X squared minus 4, and make this just to the 3rd power. Okay, we're running out of room, so I'll do it up here. Send it. F double prime of x here. All right, f double prime of x. Well, we combine our like terms. Now notice here, we have 4x to the 5th cancels and a minus 4x to the 5th cancels. That's nice. Now we have to add x to the 3rd power. We have an, don't forget the negative out here. We have negative 16x to the 3rd minus 24x to the 3rd plus 48x to the 3rd is an 8x to the 3rd. Then we got all those. So I'm going to make little marks to make sure I got everything like this. Got it? And then 96x is left over. Okay, 96x, got that as well. All right, everything in the numerator is covered. We just have our denominator, which is that x squared minus 4 to the 3rd power. And this came out pretty, well, easy, right? Or simplified. We got some more work to do, and hopefully I don't run out of room here. I might have to like come back around. We'll see. All right. So the things to worry about here for our inflection point. So I'm gonna look at my numerator and we'll look at my denominator here and see where. Oh shoot! I can simplify this one more time. F double prime of x. I got ahead of myself. Let's pull out an 8x in the numerator. It's a little easier. Minus. We have an 8x here, and I have an x squared plus 12 left in the numerator. Denominator. X squared minus 4 to the 3rd power. Let's follow my notes here, Sean. All right. So now let's go set the numerator. There's values where we get equal to 0. All right, we set the numerator equal to 0, find some points of inflection, same with the denominator here, looking at it. So we know the numerator has 8x and then x squared plus 12. So if I set 8x equal to 0, x equals 0, that's an easy one right there. X squared plus 12 equal to 0. Okay, subtract 12 to both sides, x squared equals a negative 12. We get square root, x equals plus or minus square root of negative 12. And we have imaginary. Nope, can't do that. All right, so we're not going to be dealing with that one. Don't worry about that. Now the denominator equal to 0, okay, we have an x squared minus 4 all to the 3rd power equal to 0. Solving for that, third root both sides, doesn't matter to 0. X squared minus 4 equals 0, x squared equals 4, and x equals, we square root both sides, plus or minus 2. Okay. So we got a lot going on here. Where can I fit this in? I think I can probably fit it in over here. I still have my information written. So I'm going to put all of our values in our little table here. I guess, well, yeah, I'll fit it over here. So we have a little table. Like so. We have values at negative 2, 0, and a positive 2 here. Okay? And we're going to plug in values, okay, that are less than negative 2, between negative 2 and 0, 0 and 2, and greater than 2. And these are these values right here. So I can circle here to help you out there. Okay. All right, so I picked values into my second derivative. Let's mark that right here so you know where that is. All right, so I picked a value, f prime, I'll put it down here actually, f double prime of a, what did I pick, negative 3? Yeah, negative 3. And that equaled a 4.032. I just care that it's positive and we're concave up there. I found a value between negative 2 and 0, which was negative 1. So f double prime of negative 1 is equal to a negative 3.852. It's negative, that's all I care about. Concave down. Between 0 and 2, I found f double prime of positive 1, and that came out to be 3.852, all right, and that is positive, so we're concave up here, and at 2, or greater than 2, I picked 3, so I said f double prime of 3, and that is a negative 4.032. That's a negative value, we're concave down here. All right, so now here's actually the tricky point, the tricky part here, okay? Let me find where my notes are here. There we go. All right. So we're discontinuous at -2 and 2. That's we have asymptotes. And so those values aren't actually our inflection points, even though we change concavity. It's not an inflection point. The only inflection point we have, inflection point, is right there at 0, we change concavity. At x equals 0, right here. Okay? Either -2 and +2, we change concavity, but it's not an inflection point because there's asymptotes there. We're discontinuous there, so we can't have a point of inflection there. We're concave up on our interval from -∞ to -2, and from 0 to 2. We're concave down from -2 to 0, right? -2 to 0, and from 2 to +∞. All right. So again, our final answer here is we're discontinuous at x equals -2 and +2. Our inflection point is only at x equals 0. We're concave up from -∞ to -2 and 0 to 2, and concave down from -2 to 0 and 2 to +∞. We're given this problem right here. Y equals 5x plus 30 all to the 2/3 power, and we have to find the points of inflection, discontinuities, intervals with the functions concave up and concave down. Now, right here, we have a third root function here, okay? And that's the only thing that would cause an issue here is taking the third root. But that we can plug in any x value we want, and it doesn't cause any jumps or anything like that. So right off the bat, we know what we know about these functions here, essentially the third root, and then we're squaring it. We have no discontinuities exist. So no discontinuities exist here. Now, to find my inflection points and where we're concave up and concave down, we need to find the second derivative and do the second derivative test. So let's go find the first derivative first. F prime of x here, power rule, 2/3 comes down. Keep the inside, 5x plus 30. Subtract the exponent by 1, we have a -1/3. Multiply the derivative inside, 5. Simplify this out here, f prime of x. I'm going to keep the exponent as a negative though, but 5 times the 2/3 is a 10/3, and we have a 5x plus 30 all to the -1/3 power. Now let's go find the second derivative. So we find f double prime of x here, again 10/3 out front, but we're multiplying that by a -1/3 that comes down. Power rule here, keep the inside the same, 5x plus 30. Exponent subtract by 1, okay, and we have a -4/3 times the derivative of the inside, which is just 5. Now we can simplify this whole bad boy out here, f double prime of x. 5 times 10 is a 50, but we have a -1 up top as well, so we have a -50 up top. Over, squeaky squeaky here, 3 times a 3 is that 9, so we have 3 times 3, we have a 9 here in the denominator. Then we're bringing this 5x plus 30 down to the denominator, and it's be positive, and so it's going to be the third root of 5x plus 30 all to the 4th power. Okay, we got our derivative there. All right, so now we have to find where our denominator is equal to 0 and see what happens there, okay, with our second derivative. So I take my second derivative, my 9, and that's the third root here of a 5x plus 30, all to the 4th power, and set it equal to 0. Well, I divide both sides by 9, doesn't really do anything, and I take the 4th root and 3rd power of both sides because it's all going to 0, doesn't do anything. So we really have, the issue happens at 5x plus 30 equals 0. From there, subtract 30, 5x equals a negative 30, and x equals a negative 6. So negative 6 is where we have to do our test. All right, we do our second derivative test here at negative 6. Okay? And I'm going to pick a value less than negative 6 and greater than negative 6. So I pick negative 10, and then f double prime of negative 10, we're plugging into the second derivative right here. Okay? It came out to be a negative 0.016. I just care that it's negative, and we're concave down here. Okay? Now from there, I had to find the value that's greater than negative 6. So I picked f double prime of, I picked 0 here, and it came out to be a negative 0.0596. I just care that it's negative, and again, concave down. So what happens here? We have a concave down that's happening on both sides of negative 6. So we don't actually have an inflection point. So we would say no inflection points exist. Okay. Now, where is it concave up? Well, nowhere. We didn't find anywhere it's concave up, so concave up. No intervals exist. What about concave down, which we have? Now notice how I'm going to write this. Concave down. My marker doesn't die on me here. And we have the interval from negative infinity to negative 6. That's a negative 8, Sean. Negative infinity to a negative 6. And from negative 6 to positive infinity. We just separate that right there. Okay? And now we're done. So our final answer here is no discontinuities exist. No inflection points exist. We're concave up on no intervals exist there, but concave down from the interval from negative infinity to negative 6, and from negative 6 to positive infinity. We're given this problem right here. Y equals a negative 3 over 16 times x minus 1 to the 4/3 power minus 3/2 times x minus 1 to the 1/3 power plus 2. And we define points of inflection, discontinuities, intervals of the functions concave up and concave down. Now, one thing I notice here, we're taking the 3rd root. That's the only thing that's really going on here that could cause an issue. But that's 3 in the denominator of the exponent. But there's no values that we cannot plug in. There's no jumps going on what we know about these functions. So, we can say right off the bat that no discontinuities exist. No discontinuities exist. Okay. Now, we need to find the first derivative and the second derivative to find the rest of our information. So let's go find the first derivative here. Let's go f prime of x here. All right, first derivative. Well, negative 3 over 16 stays up front. We bring down the exponent, 4/3. Multiply that by the inside, x minus 1. Subtract the exponent by 1. And we have a 1/3 going on here. Multiply by the inside, which is just 1. Minus 3/2 stays up front. Multiply by the exponent, 1/3. Inside stays the same, x minus 1. Exponent 1/3 gets subtracted by 1, which is a negative 2/3 now. Multiply by the inside is just a 1. And the derivative of 2 is just 0. Okay, let's go clean this up a little bit. F prime of x equals, well, the 3's cancel right here. 3, 3, 4, and the 16 become a 4 right there. Okay, so we just have a negative 1/4 out front, x minus 1 here to the 1/3 power, and don't worry about that 1. Minus, well, the 3's cancel here as well, and so we have a 1/2 times x minus 1 to the negative 2/3 power, and we just have the 1, don't really need it. All right, we have our first derivative. Now, let's go find the second derivative. And I'm purposely keeping it separate right now because, well, that's the way I like to look at it and see it. Second derivative here, f double prime of x. Okay, f double prime of x. All right, we have a negative 1/4 comes down here. Then we have the 1/3 comes down, 1/3, x minus 1, subtract the exponent by 1, and we have a negative 2/3 here. Times the derivative inside, which again is 1. Minus 1/2 times this exponent, negative 2/3 comes down. X minus 1, subtract the exponent by 1, and we have a negative 5/3 in the exponent, times the derivative inside, which is 1. Let's go simplify this where we can. Let's go, I'm going to move over here so I have a little more room. F double prime of x here. Well, let's make this as a fraction. Negative 1/4 and 1/3 is a negative 1/12, right? So we have a negative 1 in the numerator, and we have a 12 down here. I can bring this down to the denominator now, and we have x minus 1 to the 2/3 power, and it's a positive 2/3 power. I don't really care about that one here either. Subtract, well, the 2's cancel. That's always nice. And actually, we're going to be adding, because we have a negative, negative becomes a positive. Positive here. So we have 1 in the numerator left over, and we have a 3 left in the denominator, and we have an x minus 1 to the positive 5/3 power. Okay. So what can we do here? Well, I want to combine this to be one fraction, okay? And just like any fractions, we're going to do the same process. It's just a little more difficult. We have to find a common denominator. So I take my f double prime of x. I'm going to rewrite this function, but give myself a little space here. Equals a negative 1 over a 12, x minus 1 to the 2/3 power. And I'm going to multiply this by a x minus 1 over an x minus 1. Plus, right-hand side, I have 1 over 3x minus 1 to the 5/3 power. I'm going to multiply this one by just 4 over 4. Notice 4 times 3 is going to be that 12. We'll match up there. And then x minus 1 is like the 3 to the 3/3 power, right? Out of the exponents, we have the 5/3 power. So we can write this as one big old fraction now, f double prime of x here. And that comes out to be negative 1 times x is a negative x. Negative 1 times a negative 1 is a positive 1, plus 1. Plus 1 times that 4 is going to be the numerator. We have plus of 4 here. Okay. All over our denominator, which is just going to be a 12, x minus 1 to the 5/3 power. Keep simplifying that. We have f double prime of x here. All right. And we have a negative, well, negative x, and then 1 plus 4 is 5, negative x plus 5 here, and the denominator stays the same, 12x minus 1 to the 5/3 power. All right, we got the second derivative here, kind of looking nice and neat. Let's go find points of interest here, critical points here. So negative x plus 5, I'm going to set that numerator equal to 0, so negative x, let's separate this out just a little bit, negative x plus 5 equals 0. And that comes out to be, well, x equals a positive 5. What about the denominator? Same thing. I'm going to do that 12 x minus 1 to the 5/3 power equal to 0. Divide both sides by 12. Take the power both sides to the 3/5 power. It's just 0 here. And we're left with just an x minus 1 equals 0. And x equals a positive 1. So we have 2 points of interest here to do our second derivative test. We have it at 1 and at 5. That's really what's going on here, these two values. I'll circle them here for you. After all that, that's all we're really caring about. So we're going to plug in values into our second derivative, which we found right here, our second derivative, and see where they lie in our second derivative test. So I found f double prime of 0, and that came out to be a negative 0.4167. It's negative, that's all I care about, meaning we're concave down here. Between 1 and 5, I picked 2, so f double prime of 2 came out to be a 0.25. I just care that it's positive, and we're concave up here. Lastly, I pick a value bigger than 5, and I pick 6. F double prime of 6 came out to be a negative 0.0057. I don't care what it is, it's just negative. And it's concave down. All right. So we have inflection points at 1 and 5. So our inflection point at x equals 1 and 5, because look, we are changing concavities at 1 and 5. Good to note there. Okay. Now we're concave up from 1 to 5, so we're concave up, and the interval from just 1 to 5, but we're concave down on the interval from negative infinity to 1, and from 5 to positive infinity. And so again, our final answer here is no discontinuities exist. Our inflection point is at x equals 1 and 5. We're concave up from 1 to 5, and concave down from negative infinity to 1, and from 5 to positive infinity. We're given this critical thinking question. Sketch a continuous curve y equals f of x, where f of 1 equals 0, f prime of 0 equals 0, f prime of 2 equals 0, f double prime of x is less than 0 for when x is less than 1, and f double prime of x is greater than 0 for when x is greater than 1. Okay. When I first start with these, let's go with what we know specifically. They tell us right off the bat that f of 1 equals 0. So let's call this point right here 1, and they say, hey, we have a point f of 1 is equal to 0. We got a point right there. All right, so we got that covered. Now they tell us that f prime of 0 equals 0. What that's telling me is that we have a horizontal tangent right there. Horizontal tangent right there at f of 0, f prime of 0 equals 0. So we got a horizontal tangent going on there. And that's where the first derivative crosses 0, right? X-axis. The same thing here with f prime of 2 is also 0. We have a horizontal tangent as well going on there, because the first derivative is equal to 0 when x is 2. Okay. Now they tell us also that f double prime of x is less than 0 for when x is less than 1. And that tells me that we are concave down in that interval. Remember the second derivative test. If it's less than 0 on an interval, we're concave down. Same thing here, we're concave up. F double prime of x is greater than 0, aka positive, where the other one's negative, this one's positive, for when x is greater than 1. So we're concave up here. Okay. So what's going on? Well, we have a horizontal tangent, right, at 0 and at 2. But we're concave down from negative infinity all the way to 1 right here. And that's going to be our point of inflection. So watch this. I'm going to pick a point. I'll put it up here. I'll say, let's call that 2. And then let's call down here negative 2. Okay. So we have a continuous function. It has to be continuous forever. So let's go with the basic polynomial here. We're concave down, so we're coming up like this, concave down, but horizontal tangent going on right there. So we're changing the slope of the tangent line from positive to negative, and we're still staying concave down right here. We have a tangent line right there, 0, perfect, coming down, and then making it even here. Point of inflection happens at 1, goes down here, and then right at 2, we should have another horizontal tangent, so that's where we're going to change from negative to positive, right here at 2, right? And then we're going to come back up to positive infinity. Now notice here on our intervals, we're continuous at everywhere, negative infinity to positive infinity. Right here, we're concave down, and we're concave up here on our interval from negative infinity to 1, and then concave up from 1 to positive infinity. We have a point of inflection right there at 1. It's kind of happening. Don't really need that, specifically called point of inflection. Maybe not for my graph specifically, but f of 1 equals 0, we're good. We have a horizontal tangent here at x equals 0, right? Horizontal tangent, and as well as at 2. And so now we have just sketched a graph that matched all the requirements, that is continuous, f of 1 equals 0, f prime of 0 equals 0, f prime of 2 equals 0, f double prime of x is less than 0 for when x is less than 1, and f double prime of x is greater than 0 for when x is greater than 1. I hope this video was helpful for you. And if it was, please subscribe to this YouTube channel, like this video. This helps us make more free math lessons for you, for everyone else. So as always, thanks for watching.
Minute Math. When you need help, you use Minute Math.